All right. Well, now we've talked about the basic principle of the laser, okay, at a nice elementary introductory level. And I'd like to talk now about some different types of lasers. One or maybe two will be familiar, and the other one probably won't. We're going to talk about, about a helium neon laser, a semiconductor diode laser, and then a ti-sapphire laser. And once we talk about that, then we'll talk about mode locking and how short pulses are created. Hang on. Okay, a few moments ago, we talked about achieving population inversion in a 4-level system, like this one here. Now, let's take a look at the helium neon laser. So here's a helium neon laser with the cover taken off. It's called a helium neon because the gas inside of the laser is a mixture of helium and neon. An electric current is passed through the gas, which makes it fluoresce, and which excites the atoms. And predominantly, we're exciting helium atoms from their ground state to different excited states. Okay? Now, we don't get lasing in helium because it's just not set up for that. It doesn't work very well. But something interesting can happen. The energy levels of the helium atom match some of the energy levels in the neon atom so that energy can be transferred collisionally, meaning that the helium atoms will collide with neon atoms and preferentially excite the neon atoms to these states or to this state up here. Okay, let's focus on this one. So we're preferentially pumping the neon atoms into this upper state by collisional energy transfer from the helium atoms. Once these are in this upper state, they can relax through a lasing transition to this state here. So notice we're here. And then from this point, and emit light at a wavelength of 632.8 nanometers. From this point, there's rapid relaxation down to lower states and finally down to the ground state of neon. So this is a rather complicated looking, but still nonetheless, 4-level system. The primary excitation excites helium atoms from their ground state up to this state. Oops. Energy is collisionally transferred to the neon atoms. And now we have a light-emitting transition. We develop a population inversion between this state and that one. And then we get rapid de-excitation from the lowest level back to the ground state. Most helium neon atoms that we see operate at 632.8 nanometers. But there are actually other laser transitions. These can be set up to operate in the infrared at 1.15 nanometers, or longer in the infrared at 3.39 nanometers. 3.39 microns, 1.15 microns, and 3.39 microns. Those are both wavelengths in the infrared. Not shown here, helium neon lasers can also be made to operate in the yellow part of the spectrum. Okay, so the pump here is an electrical current. The mirrors are at the front and back end of the laser, and that's the helium neon laser. Here's a schematic picture of a semiconductor diode laser. In a semiconductor, like gallium arsenide, we have bands of energy states. We have the lower band, which is normally full of electrons, called the valence band. And we have the upper band, called the conduction band. And we set up a structure called a PN diode, where electrons can be injected into one side in the conduction band, which is normally empty. And then they can recombine and in this section. Let me be a little more clear because I see I'm missing some of the details so far. In a semiconductor diode laser, we don't simply have a diode, electron rich on one side and electron deficient on the other side. We have something else too. We actually have a sandwich of a low bandgap semiconductor, gallium arsenide, between two high bandgap, larger bandgap semiconductor layers that are aluminum gallium arsenide. this makes a kind of well or trap for the electrons and for the holes, the empty orbitals here. And that makes recombination especially preferential. Okay? So this is another type of laser. It has some nice properties. First, you can see that it is a 4-level laser. We're injecting electrons in the upper state. They collect in a long-lived intermediate state. They make a transition down to this state. And then the electrons drop down still lower into the, fill the holes in the valence band of the large bandgap semiconductor. What's nice about this is that it's directly electrically pumped. Also, it's a solid, which makes it very compact. The density of atoms is very high, so the whole laser can be very small, as small as a grain of sand, and yet still have as many atoms emitting light as there were in the helium neon laser. Also, because it's solid, if you drop it, it won't break, whereas this one looks kind of fragile. Okay, the last laser I want to talk about is the most complicated, but these are the lasers that are in my lab, so I want to focus on them. This is a titanium sapphire laser. In a titanium sapphire laser, the active medium is sapphire, aluminum oxide, which is inert. But embedded in the sapphire are titanium atoms, and the titanium atoms, rather like the neon atoms in a helium neon laser, this is where all the action takes place. The role of the sapphire is to broaden the energy levels of the titanium atoms into bands in a solid. The interaction between the atoms broadens the discrete levels into bands. And we'll see why that's important in a second. So in such a laser, here's the active material, the titanium sapphire. It's being pumped with light from a green laser at 532 nanometers. The green laser is going through this mirror and exciting the titanium sapphire crystal. Then we have the crystal, and it's surrounded by mirrors. But in this case, which actually is the diagram of one of the lasers in my lab, the layout of the mirrors looks a little complicated. There's a high reflector here, and there's a partial mirror or an output coupler here. And then there are some other mirrors whose sole purpose is just to fold up the laser cavity so that I can have a very long laser cavity in a small box. Okay? This arrangement is sometimes called a bow tie arrangement. But that's essentially what it does. After the laser, there are some other things which we'll talk about in a second. So they condition the beam. So first, how does this laser work? Well, as I mentioned, the sapphire atoms has electronic energy states. Here's the lowest. Here's the next electronic energy state. But it's a little bit more complicated. First, there's actually a band of energy states here, not just a single discrete energy level. And likewise, a band here. But there's something else. The location of the energy band depends on exactly the position of the titanium atoms in the crystal. They're in the lowest energy state, the stable position of the titanium atoms here. But when they get promoted to the excited state, they're actually no longer in the lowest energy equilibrium state for that configuration. For the excited state, the lowest energy equilibrium state is here. So the atoms are excited, but then they relax. The titanium atoms actually shift over slightly, and we're here. From this point, they can make a transition down to the lower electronic state, and they'll end up here. But now the titanium atoms have to relax back to their original positions, like so. So this is also a 4-level system, but it's funny because we actually only have 2 levels. They're just shift around as the crystal relaxes. So we pump the crystal here with green light from there to there. It relaxes. It drops back down by emitting red light, and then it further relaxes here. These relaxation steps happen very, very rapidly, in something like 10 to the minus 14 seconds, a time on the order of 1 period of oscillation of the vibrational modes of the crystal. So these steps, the relaxation steps, are extremely fast, And that makes the whole 4-level scheme work very, very well. Another thing is that these two transitions, both the absorption transition and importantly, the emission transition, these are transitions between bands of states. So the light that comes out is actually spread over a range of energies. Okay, it's not perfectly monochromatic like the helium neon laser. Instead, there could be emission over a band of wavelengths. That's the titanium sapphire laser, okay? Now, as I said, a little bit complicated, but it's really important that we get emission over a band of states. And that's because that allows us to mode lock the laser. That's the next thing we'll talk about, okay? Okay, so now imagine we have this light at many different wavelengths that's bouncing back and forth between the mirrors. And I haven't drawn in the amplifying stage, but we know that it's there, right? This just is an illustration. So this is my laser. Now, if the system is just operating normally, then light will come out of the laser, you know, at a steady rate. It won't be pulsed, it'll be continuous wave, steady power, okay? But this isn't the only way that I could do things. I could arrange so that instead of having continuous beam coming out, I could have short pulses. And this is how this works, and here's how this works. I can put into the cavity, along with the amplifier, I can put in something called a saturable absorber. A saturable absorber is an absorber that can absorb light, but when the intensity is high enough, it becomes transparent. It can't absorb anymore, okay? So when the laser is operating normally like this, if I put in the saturable absorber, because the power inside of the laser is relatively low all the time, the saturable absorber will absorb a lot. But if there's a little fluctuation, one of these fluctuations, so that the intensity is a little bit higher at one moment in time, well, that fluctuation won't be absorbed as strongly by the saturable absorber because of the saturation. It's a little bit more intense, so it's getting closer to the region where the saturable absorber is transparent. And so that little pulse will go through, it'll pass through the amplifier, pass through the saturable absorber and not be attenuated much, reflected back, and do this again. So compared to the background light, the light in the more intense pulse will get amplified more. Or it'll get amplified and there'll be less loss. So when it hits the end mirror and comes back through again, this process will repeat and the pulse will get amplified even more compared to the background. And very rapidly, we'll end up in a situation where all of the light is bouncing back and forth as one giant pulse. The laser is said to be mode locked. And this giant pulse can occur because we have many different wavelengths, such that if we arrange the phases of the waves just right, they'll add together to make a giant pulse. So now the laser is bouncing back and forth. Every time the laser pulse strikes the partial mirror at the front of the laser, a laser pulse is emitted by the laser. And so we get a stream of narrow laser pulses. And the time between the pulses is just the round trip time inside of the laser. So if we want to make this not too short, then we need to make the round trip time in the laser long. Going back for a second, that's why we have this long folded cavity inside of the laser. We want to make the rate at which pulses come out relatively long. When this is operating in pulse mode, there's a single pulse that oscillates back and forth between the output coupler and the end mirror, M2 here. Okay? And in this case, it takes about 12 nanoseconds is the round trip time inside of the laser. And so we get about 70 or 80 pulses million pulses per second out of the laser. Okay. Well, I think we'll stop here. Oh, I'll just show you one more thing. I have a second laser in my lab. In that case, the power is much higher, and we want to have a lower repetition rate. We want fewer pulses per second so that the pulses will be more intense. And so to do that, we want a very, very long distance between the end mirror, saturable absorber here, and the output coupler, which is over here. And so we're using a multi-pass mirror, which essentially makes the path length about 50 meters from this end of the mirror to that one. In this one, you can also see the saturable absorber. It's built into this mirror, the SBR, saturable reflector. And this is the element that allows the laser to operate in pulse mode. Okay, well, let's stop here, all right? And of course, you can take any questions you have to me.